Good morning, geometry students. I am in yet another all-morning meeting, so unfortunately I will not be with you this morning. But as always, geometry will go on. Luckily, today's lesson is pretty short and sweet, pretty simple. What we're going to do here is I'm going to take you through the slides that you should already have, that you already should have been given by the sub. So you should not have to do much writing. I'll take you through these slides in about 10 minutes with a couple of example and practice problems that you can do along with me. As always, I will give you some time to do some of these problems on your own. And then at the end, I'm going to show you your homework problems, and I'm going to do a couple of examples from your homework that will be a part of your homework as well. But we'll get to that at the end. So for now, go ahead and get out your notes, have a pencil or pen ready, and we will jump right in. So as you can see on the board, our learning goal for today has not changed from yesterday. We are still on the quest to be able to say that you can prove that triangles are similar. And if you remember, yesterday we learned a few ways to do that. Really quickly, I'll write them up here so that you can see them. We learned AA similarity, which was angle-angle similarity, which remember means that if I have two angles that are congruent between the two triangles that I know are congruent, then we can say that the two triangles are similar. We have SSS similarity, which remember was not saying that the sides were congruent, but just saying that the sides were proportional. If I knew nothing else about the two triangles, but I knew that their sides were proportional, then we could also say that they're similar. And then, of course, we learned SAS similarity, which was if I know two of the sides are proportional and the angle that is formed by those two sides, then I can say that the triangles are similar. So remember, that's where we have to this point. Those are the tools that we have in our tool belt. And we're going to add a few more tools to that today. Just a quick reminder of what it means for two triangles to be similar. It means that if I have these two triangles here, that if these two triangles are similar to each other, it means that all of their angles are congruent, and all that's corresponding angles. I'm going to have to draw 3 tick marks there. And it also means that their sides are proportional. So the relationship between these two sides will be the exact same as the relationship between these two sides. And that relationship will be the exact same as the relationship between these two sides. So just a quick reminder of what it means for two triangles to be similar. Corresponding angles are congruent, corresponding sides are proportional. And now we continue on. So theorem 8.4, the triangle proportionality theorem, says this: if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. Here is what that means. We have a line right here. I'm going to trace over it really quickly. There's the line that I'm talking about. That line, if that line is parallel to one side of a triangle, see how it is parallel to this side. So here we have a side of a triangle and we have a line that is parallel to that side. So that's what this theorem is talking about. And that line that is parallel intersects the other two sides. So once again, we have one side of our triangle here, and we have a line that intersects the other two sides at these intersections right there. If we have a line that intersects the other two sides, then it divides the two sides proportionally. So what it says is that any of the parallel lines that are formed here, as we see here, divides these lines proportionally. So AE, which is 4, divided by EC, which is 12, will be the same as AD over DB. This proportion will be the same. So let's go ahead and plug in what we know and work this out. So 4 over 12. AE is 4. We can see that here. EC, this distance from this intersection to there, is 12. So we can plug in 12 for that. That is going to equal AD, which is x, we don't know that, over 15, which is dB. And then, of course, you can see that we can cross multiply and solve. I could also just look at this and say, okay, 4 over 12, that's going to reduce to 1 over 3. So what could I plug in for x that would give me the same relationship as 1 over 3? Well, 15 divided by 3 is 5. So x is 3. And once again, you could get there just by eyeballing it or by seeing, or by going ahead and cross multiplying and solving. So pretty simple stuff. If we have two parallel lines that are within the same triangle, it divides those sides proportionally. We will come back to that in a practice problem in a second. Moving on, the converse of that statement says this: if a line divides two sides of a triangle proportionally, then it is parallel to the third side. So now you can see in this example, we don't know that the lines are parallel. It does not have the parallel marks that I'm adding now. Okay, we do not know that. But what it does give us is these parts of this triangle. And what we can see is that there are the exact same values as up here, and that 4 over 12 is in fact the same ratio as 5 over 15. They both reduce to 1 over 3. And because these are proportional, because the sides are proportional, just like we see up here, that by nature means these lines have to be parallel. So what is the difference? And this is something I think we have a hard time with sometimes in our geometry classes. What the difference is here we're proving that the sides are proportional. Here we would use theorem 8.4 to prove that these sides are proportional. Down here, however, we are not proving that the sides are proportional. We can see that right away because it gives us this info. What we're proving down here is that those two lines are parallel. Okay, so that is the converse. Once again, moving right along, theorem 8.6. If three parallel lines, here you can see that this line AD is parallel to this line BE is parallel to this line CF. If three parallel lines intersect two transversals, so we have one transversal right here and we have another transversal right there, then they divide the two transversals proportionally. So basically what this is saying is that any way that I divide up these transversals will form a proportion. So you can see over here we have written two examples of proportions. AB, this distance here, over DE, the ratio that is formed by the lengths of those two parts of these transversals will equal the ratio between BC and EF. Or I can say similarly that AB, this section here, and the ratio of that side to this side will be the same as this relationship between DE and EF. Notice, these are two different proportions. We're comparing two different things, but we know that in both of these cases, these proportions will hold true if we have three parallel lines cut by two transversals. So I can compare this length right here to this length right here, and this length right here to this length right here, or I can compare this length right here to this length right here, and this length right here to that length right there. Okay, so that is theorem 8.6. Once again, we're going to move right along. This is the last theorem we're going to learn today before we do some practice problems. Theorem 8.7. If a ray bisects an angle of a triangle, once again, remember what bisect means. Bisect means cuts it perfectly in half. So here we see this ray bisecting this angle. It creates two equal angles because it cuts it perfectly in half. If this angle measured 50, these angles would be 25 each. If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are, guess what, proportional to the lengths of the other two sides. So you can see here's the ray. I'm going to trace over it in green right here. Here's the ray. It divides this half into two parts, AD and DB. And what this theorem says is that this ray divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides of the triangle. So this side AD is going to be proportional to this entire side over here AC at the same rate that this side DB is proportional to BC. Once again, but that's not the only proportion that is true. We could also say that AD over BD is the same proportion as AC is to BC. So basically what we've learned here today on this first slide and this second slide is lots of ways to create proportions in other geometrical situations. In other situations where we're dealing with triangles, or where we're dealing with parallel lines, or where we're dealing with bisected angles. There are lots of proportions that we can know are true. What we're going to do is we're going to take a couple of those and put them into action. So here we have a couple of example problems. This picture looks just like our first theorem here, theorem 8.4. So chances are we're going to be using theorem 8.4. Remember, theorem 8.4 said if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So here we have two parallel lines, and what we know is that it divides these sides proportionally. So into what proportion? Well, we know that this ratio 4/8, the ratio of this section to this section, is going to be the same as the ratio of 6/x. Once again, we could cross multiply and solve this, and you would get that x equals 12. But you could also just see, oh, well, 4/8 reduces to 1/2, so what could I plug in here for x that would give me the same ratio? Well, 6 times 2 is 12, so we could figure out that x would be 12 that way. Now if you look at this, once again, looks like we have a ray that is bisecting an angle, so we need to go back here and look at theorem 8.7. And remember what theorem 8.7 says is that this ray, because it bisects this angle, divides the opposite side into proportional segments. So there are actually a couple of proportions that we could set up here, and I'm actually going to set up both of them just to show you. We can see that we're given that this whole side is 14, and that this little segment x we have marked as x. So the two proportions we could set up here, remember it's the exact same picture is right here in theorem 8.7. So you could just copy this down and then plug in what we know. And in fact, I'm going to do that. We have that AD over AC is going to be equal to DB over BC. That is one of the proportions we can set up in this situation. The other one that we can set up is this. The comparison between the two sides that are cut in half. That's AD and DB is going to be the same as the relationship between the two other sides of the triangle, which is AC and BC. Either way, I could plug in and solve for x. Which way would be easier? Well, it doesn't really matter. Both ways would have a same level of difficulty, but what we're going to do is we're just going to go ahead and do this first one. But if you want some extra practice or you wanted to, you could also plug into this proportion and cross multiply and solve just to double check that it worked. Okay, so AD, clearly we have demarcated AD as this length x, so I'm going to plug in an x for AD. DB, now this is a little bit trickier because it doesn't give us an exact length for DB, but what we do know is that this whole side AB is 14, and I could represent this length DB by saying that DB is going to be this whole length 14 minus whatever this distance is x. If I take whatever this distance x is and I subtract it from this 14 number, that is going to give me this DB length. So that is one way that I could represent DB, and that is how we're going to write it. That 14 minus x is going to represent the length of DB. So you can see we actually have two variables. This variable shows up twice in our ratio. That's going to be proportional to AC over BC, which is AC is 9 and BC is 15. And I actually lied. In the middle of doing it, realized that I've done this proportion when I said I was going to do the top one, but the same idea follows. So now we can cross multiply and solve. 15 times x is just 15x. And then I'm going to take 9 and multiply it by all of 14 minus x. And then I need to distribute this 9. I don't know what 9 times 14 is off the top of my head, so I'm going to pull up my calculator. 9 times 14 is 126. Very good. So this is 15x equals 126 minus 9x. I need to add this 9x over, so I'm going to add 9x to both sides. That will cross this out over here when I add 9x to this side. 15x plus 9x is going to be 24x. So I have 24x equals 126. So I need to go back to my calculator and divide 126 by 24. And that gives me 5.25. Okay, and if you did this proportion up here, you would get the same answer. All right, moving right along. In the diagram, angle 1 is congruent to angle 2 is congruent to angle 3, and PQ equals 9. QR equals 15 and ST equals 11. What is the length of TU? Well, look what we have here. These are parallel lines, but look, it doesn't say they're parallel lines. How do we know that they're parallel lines? Well, we have these three angles here, which are all corresponding angles, and they are congruent. So if you remember way back in chapter 4 or 5, we learned that theorem that said if the corresponding angles are congruent, then the lines are parallel. So we can say that all of these lines right here are parallel. And then we need to come back to theorem 8.6. Sorry, that's my phone. And look at what this theorem says. If three parallel lines intersect two transversals, then they divide the two transversals proportionally. So once again, we could set up either of these proportions. I'm going to do, let's see here, I'm going to do this first one just because my brain seems to, I'm sorry, I'm going to do the second one just because my brain seems to see this one easier that way. Maybe you'll agree, maybe you'll disagree. But you can see we don't know, we're looking for this length TU, so I'm going to plug in an x for that length TU. One way I can use this theorem is just to compare this side to this side and that proportion of this side to this side. So the proportion of this side to this side is just going to be 9 over 15. And that's going to be proportional to 11 over x. And then I have to cross multiply and solve, or divide by both denominators and solve. 15 times 11, let's see here. 15 times 11 is 165. And then I need to divide 165 by 9. And we get that x is 18.3. So there you have it. X is 18.3. And you can see that, that if I had done it the other way, I would have done 9 over 11 equals 15 over x. And look, we would have been doing the exact same math, multiplying 15 times 11, multiplying 9 times x, and then cross multiplying and solving. So there is that. So now what we are going to do is I went ahead and wrote your homework assignment on the board. You can see on your homework assignment that I have listed a lot of odd and even problems on there. I did that for one of a few reasons. What I'm going to do is we will grade this homework on Monday, but you will get half credit for doing all of the odd problems. So there are 8 problems right away. You should all get a 4 out of 8 if you have done and completed all of the odd problems. I don't care if they're correct. But then what we'll do is we'll also grade the even problems to round out that grade. So you'll get a 4 out of 8 just for doing the homework, and then every one that you get correct after that will get you some more points. So what I'm going to do here is I'm going to go ahead and do the first odd problems of this homework for you. And so you can go ahead and open your book. I'll give you a couple of seconds to do that. Open your book. You can go ahead and write down your homework. You can go ahead and write your name on your homework, write down the problems. And then we're going to do the first odd problem of each section. So as you can see, your homework is going to, as it says on the board, is page 502, 11 through 14, and 21 through 24, I believe. Yeah, that's right. And you have to do all 8 of those problems. We will grade the even ones, and you will get credit just for doing the odd ones. And what we're going to do now is we're actually just going to go ahead and do the number 11, and we're going to do number 21. So by the time you leave class, you will already be 1/4 of the way completed with your homework. So I'm going to give you about 15 seconds of silence in the video to do that. So you go ahead and get your homework ready and your book out. And then we will start number 11. So take a couple of seconds and do that. Okay, so hopefully you are ready now. We're going to go ahead and jump in. You can see my friends' text message group popping up here, I'm sure. Yes, one of my friends named our text message group the Wolf Pack, so you can make fun of me for that later if you'd like, but they are excitedly cheering about how the Hawks just came back from down 20 to beat the Rockets in the 4th quarter. So if you were wondering what that was about, that was that. I apologize. But moving right along. Okay, here are the instructions for number 11, logical reasoning. Determine whether the given information implies that QS is parallel to PT. So here is this picture. Here's QS, here's PT, and what they want us to do is to see if these lines are parallel. Well, if you go back to the first theorem that we learned today, and remember the converse said that if these sides of these triangles are proportional, then these lines will be parallel. So coming back to number 11, we just have to see if the sides of these triangles are proportional. You can see we have 2 triangles here. And the proportion that we can set up is QR, this section over here is 16. And you can see this little section over here is 4. That's going to reduce to 4 to 1. And that's going to be proportional to 8 over 2. Ah, look at that. We have 2 ratios that will reduce to the same ratio of 4 to 1, so these are in fact proportional. And so the answer to this one, to number 11, would be yes. QS is parallel to PT. Explain. Our explanation here would simply be this. If I go back to theorem 8.5, a line divides 2 sides of the triangle proportionally. So we could come back and say yes, and then your explanation would be something like this line QS divides the sides of that triangle proportionally, and that would be your explanation. Okay, so that's number 11. Pretty simple. You're going to do something very similar for 12. 13 and 14, you're going to see if these lines are parallel to each other just by seeing if these are proportional, if these ratios work, or if they don't. So pretty simple stuff. Now we're going to move along, going to go ahead and do number 21. So if you look at number 21, it says find the value of the variable. Well, now we're actually dealing with the exact same type of problem, except now these lines are parallel. It shows us that they're parallel. So what that means is that these sides are going to be proportional. Okay, so we're just doing basically the opposite of what we just did. So now, because the lines are parallel, we know for certain that 9 over A is going to equal 15 over 5. And that's a proportion that I can set up and solve, that we have now set up and that I can cross multiply and solve. So when I do that, I get 15a equals 45. 5 times 9 is 45. I need to divide 45 by 15. 15 goes into 45 3 times, so a is 3. Pretty simple stuff. Hopefully this video leaves you enough time so that you can actually go ahead and finish 12, 13, 14, and 22, 23, 24. These are pretty simple problems, not that difficult, just based on what we learned today. Have that done by Monday. On Monday, I will also take up your homework that was due today, as I'm clearly not here to take up your homework that was due today. We will grade both sets of homework then, but make sure this gets done by Monday. On Monday, I will hand you your practice test. We will work on your practice test Monday and Tuesday, and then your test is Wednesday. I hope you have a wonderful weekend. If you have any questions, you can email me. This video is clearly on Haiku, so if you need to go back and review it later while you're doing your homework, you're more than welcome to. It will stay up on Haiku. So, sorry I couldn't be with you today. Come and find me sometime later in the day as I'll be in my room, and I hope you have a great weekend. Thanks.